Thanks for coming to this video. In this video, I would like to talk about my work on bet on independence. And the first thing I would like to assure you is that this talk is not about gambling. Instead, bet here stands for binary expansion testing. So in this project, what I did was to propose a new testing framework for non-parametric dependence detection. So the problem we study here is this classical question. Can we distinguish dependence from independence non-parametrically without any information of the joint distribution? It turns out that this is not an easy problem, so we'll begin by focusing on only two continuous variables, x and y, and we'll assume that we have n ID observations of them. We'll also focus on this copular setting, in which both marginal distributions are uniform over 0, 1. We can achieve this if we know the marginal CDFs. If we don't, we can use the empirical CDF instead, and the theory and methods are shown to be similar. We study the test of independence between random vectors in this follow-up paper. Here's a list of existing tests on this problem. We can see our old friend Pearson correlation here, measuring linear dependency. We can also see that non-parametric tests are available since 1948. An important method here is the distance correlation by Shackley et al. Here. The distance correlation possesses the important properties that a zero-distance correlation does imply independence, and tests based on distance correlation is universally consistent for any fixed alternative. But people have still been developing new tests on this problem. So why do we need to study this problem for so many years and develop so many tests? This is because without any information of the joint distribution, dependence is something very hard to track. To show how complicated this problem can be, I designed this structure called bisection expanding cross. This structure can be regarded as space-filling fractal. So in the first level, this is a cross in the unit square. To obtain the second level, we take the midpoints of the four arms and extend bisectors until they intersect. We can repeat this process to obtain level 3, level 4, and so on. Here are some interesting properties of the uniform distribution over this structure. The marginal distribution of x and y are uniform 0, 1 for every level, but the joint distribution of x and y is degenerate. These properties lead to an interesting paradox. That is, whether we shall describe the uniform distribution over the fractal as strongly non-independent or nearly independent. It appears to be strongly non-independent because the joint distribution is degenerate. So if we consider the total variation distance from this distribution to the uniform distribution over the square, which means independence, the distance is the maximal possible value 1. So in this sense, the distribution is far away from independence. On the other hand, since this fractal is space-filling, we can approximate any point in the unit square from the grid lines. And for any point x and y, if we let d go to infinity, we see that this joint probability converges to x times y, which is precisely the product of marginal probabilities. Therefore, in this sense, the distribution is very close to independence. Not only this is a mental challenge, this is also a challenge to existing non-parametric tests of independence. Simulations have shown that for this fractal at level 4 here, not very complicated, the test based on the distance correlation, along with many other tests, are powerless even when the sample size is 20,000. That was a shocking fact to me. It was shocking to me because we only have two variables. With 20,000 observations, we can easily plot everything out and see the dependence through our eyes. But the distance correlation says no, we cannot distinguish it. So why is that? There are many reasons, but one important reason is this non-uniform consistency, which is summarized in this theorem. This theorem states that for the problem of testing independence against delta away from independence in total variation distance, for any sample size and any test you can think about, there exists an alternative distribution such that the test you are thinking about is powerless. This fact can be explained by the fractal on the previous page. We can think about any good test that is universally consistent, so that for any fixed alternative, the test has a power of 1 as n goes to infinity. However, in practice, we never have infinite many samples, and for any fixed sample size n, we can keep expanding this cross, until at some moment, the uniform distribution over the fractal is so close to the uniform distribution over the square so that the test you are thinking about becomes powerless. So the message from this theorem is pretty negative. No test will be able to detect all forms of dependence, not even all levels of this fractal, which is far away to independence in total variation distance. In practice, non-uniform consistency means blind spots. Every test has a blind spot for certain forms of dependence. So what can we do? This question puzzled me for a long time until I came up with my solution. If testing exact independence is not possible, I will test approximate independence, and if one test is not good enough, I will construct a sequence of tests. This approximation of independence and the sequence of tests are constructed through a filtration approach. So here's the outline of my talk. I will talk about this filtration approach, the procedure max-bet, and do numerical studies. And we'll begin with the filtration. The filtration is constructed through this classical probability result of binary expansion. Recall that we are now in a copular setting where the marginal distributions are uniform 0,1. For uniform 0,1 variables, we can decompose them into a weighted sum of binary variables, where these variables are RID Bernoulli halves, and we can apply this result to both marginal distributions. And we can truncate. We can truncate the expansion up to a certain depth d. After the truncation, it's easy to see that UD and VD are nothing but discrete uniform variables over dyadic fractions. Moreover, as d goes to infinity, it's easy to see that UD converges to U and VD converges to V in probability. But these marginal convergences do apply the joint convergence in probability. And this is important because it means we can approximate the dependence in U and V from that in UD and VD. And this approximation is apparent if we regard it as a filtration. At every level d, we learn 1a and we learn 1b. As d goes to infinity, we learn everything. So why is this filtration helpful? To see that, let me bring this famous quote from George Box. All models are wrong, but some are useful. When I write down UDVD, I know up front that this is a wrong model. UDVD is not UV, so it is clearly wrong. However, this wrong model turns out to be quite useful in many ways. The first thing it brings us is the universality. That is, although the dependency between U and V can be arbitrarily complicated, as long as d is large, we can have a good approximation. The approximation error is exponentially small. The next advantage is identifiability. Recall, the problem is hard because we can lose control. In this distribution-free setting, we don't have a model, we don't have a parameter, we don't have a likelihood, we don't have anything. However, if we consider the binary expansion filtration, then at every depth d, we have a 2D by 2D contingency table, which is a well-defined model with well-defined parameters and well-defined likelihood, so we have everything. As a consequence, we achieve the desired uniformity. That is, at every level d, we can be consistent against any alternative distribution that starts away from independence in total variation distance. Recall that this is not true without the filtration approach. Because of these three main advantages, I propose to study statistics that are functions of A's and B's. I call them binary expansion statistics. I also propose to test the approximate independence between UD and VD, which is referred to the binary expansion testing. So this is my bet on independence. A few remarks before we proceed. The first remark is that in the previous slides, we constructed the binary expansion filtration as if we knew the marginal distributions. However, even when they are unknown, we can still construct the filtration. The theory and method are shown to be similar, and here are some details. The second remark is that the binary expansion filtration is certainly not the only way to construct a filtration to study dependence. However, we consider the binary expansion approach because there are many advantages of this filtration. The first advantage is that this filtration is simple. The sigma field at every depth contains only finitely many events and is determined by only finitely many binary variables. If we consider the Fourier basis, the sigma field will look much more complicated. The second advantage is that dependency between two binary variables is linear. Two binary variables are independent if and only if they are uncorrelated. We know this is not true in general. We know this is true for bivariate normal distribution, but it is also true for binary variables. And this is good because this means we only need to focus on the second moments. The third advantage comes from the connection to current computing systems, which are based on bits, which are binary. Using binary expansion statistics allows us to work directly over data bits and to implement the statistical procedure through bitwise algorithms, which in turn provides us fast computing. We have already implemented that in this paper, and our bitwise algorithm is about 100 times faster than existing methods. Due to these three reasons, we focus on the binary expansion approach, and I would like to mention that although computer theory is well developed, we are not aware of a similar filtration approach. Now let's turn to the statistical procedure. A uniformly consistent test of independence between UD and VD is about this test of discrete uniformity. The likelihood is something we are familiar with, the multinomial distribution. For this classical problem with this classical likelihood, the classical test of chi-square test is uniformly consistent. But why shouldn't we use the chi-square test? Two reasons. Firstly, the degrees of freedom of the chi-square test is 2 to the power d minus 1 squared, which is growing exponentially, and that could affect the power. Secondly, the interpretation of the chi-square test is not clear. That is, even if we can obtain a small p-value from the chi-square test and can claim x and y are dependent, we don't know how the two variables are dependent. So these are some limitations of classical tests that we propose to improve upon. We can improve upon these two properties by grouping the cells in the contingency table through interactions of binary variables in the filtration. I will skip many theorems, but the consideration of grouping cells in the table through interactions of binary variables in the filtration will lead to a reparameterization of the multinomial likelihood. And I will illustrate this with the case when d equals 2 and there are 15 non-trivial binary variables in the sigma field. Note that each interaction of binary variables will lead to a division of the unit square into a white region and a blue region of equal area. And the new parameter, so-called the interaction odds ratio, or IOR, is defined as the ratio of the product of white cell probabilities and that of the blue cell probabilities for each binary interaction. So, what is the advantage of using these lambdas over the cell probability P? One advantage is that the separation of marginal and joint information. Recall that a cell probability P carries both marginal distributional information and joint distributional information. However, with these lambdas, we can separate them into marginal IOR and cross IOR. Note that in the sigma field, there are marginal interactions involving only A's or only B's. For these marginal interactions, the lambdas contrasting the white region and the blue region could only provide marginal distributional information. On the other hand, for cross interactions involving both A's and B's, the lambdas contrasting white region and blue region are really providing information about the dependence. Indeed, there's a theorem stating that all the information about dependence is summarized in cross-interaction odds ratio, and UD and VD are independent if and only if all the cross IORs are ones. So in this sense, the cross IORs are to contingency tables as correlations are to multivariate normal distributions. To study dependence, we should focus on these parameters. It turns out that sufficient statistics for IORs are also simple. They are precisely these so-called symmetry statistics, which are the differences between the number of points in white and blue. The namesake here is because these statistics measures the balance of points in white and blue regions. Under the norm, we expect the number of white points and blue points are similar. However, if UD and VD are dependent, then somewhere, somehow, we should see some unbalanced counts in white and blue regions. Now that symmetry statistics are sufficient for the IORs, we should construct test statistics based on them. In this paper, we consider the test statistic as the maximal symmetry statistic in absolute value, we call this test the max bet. Procedure-wise, the max bet is very simple, and we'll illustrate again with n equals 50 and d equals 2. For the same data scatter plot, we overlay the plots of the 9 cross interactions with white and blue regions, and we count the number of points in white and blue. Like for this interaction, we have 23 in white and 27 in blue. Then we look for the maximum absolute difference between the white points and blue points, which is this interaction that has 32 in white and 18 in blue. We then use the binomial distribution to find the p-value, and to use Bonferroni correction to multiply this p-value by 9 to obtain the overall p-value of the max bet. Although the procedure is simple, it turns out that its power can be minimax optimal. Here's the theorem summarizing the optimality. The only additional assumption we need here is this sparsity assumption, which I'll talk about later. Under this additional condition, we can show that the power of the max bet can be arbitrarily close to 1 if the sample size grows at this rate. On the other hand, if the sample size grows at any slower rate, if you change the big O to little o, then for any test you can think about, there exists some alternatives such that the power is strictly bounded away from 1. So in this sense, this rate of sample size requirement is minimax optimal, and the max bet attains this optimal rate. A few remarks here are that first, the sample size requirement of the chi-square test is known to be big O 4 to the power d, and this is much bigger than the rate of max bet. This in turn means that the max bet will have better power. Secondly, this condition compares the maximal E signal to the overall signal, and it can be regarded as a sparsity assumption because it can be satisfied when the dependency comes only from a few cross interactions. However, this condition is certainly more general than a sparsity assumption in L0 sense. The third remark here is that this result is consistent with existing results in the ANOVA setting, that when signals are square root sparse, the max test is much more powerful than the chi-square test. The last remark here is that the rate here implies that if we are given a sample size n, then we can go as deep as log 2n in the binary expansion filtration without losing power. Besides the improvement in power, the max bet also improves the interpretability. This is because when the Bonferroni procedure rejects independence, it returns with 50% of the area, either white or blue, with significantly more points. This pattern in turn provides interpretation of the global dependency. We shall use the fractal again to illustrate this feature. Note here that for this form of dependency, all points sampled will fall into the white regions of these cross interaction. Therefore, the p-value of the max bet at depth d plus 1 is thus 2 to the power n because all n samples are in white. This is the number of tests at this depth, and this 2 is for a two-sided test. So when n is large, this p-value can be very small to reject null, and then the white region implies the form of independency. Moreover, this answers the paradox I mentioned earlier. If we consider depth d, then UD and VD are really independent. In this sense, U and V are nearly independent. If there's any dependency, the dependency exists only in the remainder term of the binary expansion approximation. On the other hand, if you apply the max bet at depth d plus 1, then you get a small p-value here and rejects independence. So in this sense, U and V are strongly non-independent. So there isn't really a contradiction here. It just depends on which depth you're at in the filtration. Now let's turn to numerical studies. We first study the power of the test. We compare the max bet with many methods under many simulated settings. The message from the simulations is, every dog has its day. Indeed, no test can uniformly dominate another, but one thing to see here is that the best, which is the right curve, is very rarely the worst in power. Perhaps except here under this setting, where sparsity assumption in the theorem does not hold. But in general, the bet has robust good power, and this is the uniformity and the minimixity that we are aiming for. We are protected from the worst case scenarios. Now let's turn to applications in exploratory data analysis. When we analyze a small dataset, one thing we often do is the scatter plot matrix for each pair of variables in the data. However, this approach is not feasible for large datasets simply because there will be too many plots to draw. So what do people do in practice? Here's a real story from a large lab in genetics. They are working with gene expressions, so the number of variables is in the magnitude of 10,000. To do the exploratory data analysis, their first step is to test independence between each pair of variables with distance correlation. They do so for the 50 million pairs, and they rank the p-values to list the 20,000 most significant pairs. So this step has no problem. Distance correlation is a good, powerful test, and ranking p-values is certainly plausible. But here's the second step. The second step does not look so great. The only thing they can do is to hire graduate students to read these 20,000 plots one after another. I think you can already see the problem now. This is certainly not the best way to use the time of our talented graduate students. And you probably already see the reason why. Because the interpretation of existing tests are not so clear. So what I want to say here is that BET can help, which is interpretability, its speed, and its power. I would like to illustrate how BET can help us with a real-time experiment. And by calling it real-time experiment, I really mean to do the simulation right in front of you. What I'm going to do now is to simulate a dataset with 256 samples and 100 variables. For the first 10 variables, I will simulate them as 5 pairs of bivariate normals, so their dependency is linear. From variable 11 on, among the 90 variables, I will randomly pick 2 of them and randomly assign them to have one of the 3 nonlinear forms of dependency here: parabolic, circular, or sine. The goal here is to use the BET to identify the 2 variables that are nonlinearly dependent, as well as identifying the nonlinear form of dependency. For replicability and fairness and for fun, in a regular talk, I will ask the audience to suggest a random seed to start the process, but in this video, I will just generate the random seed randomly. Before we start, 2 notes on the comparison with the distance correlation here. First, recall that it's not easy for the distance correlation to do the task because its interpretation is not clear. How to distinguish linear dependency and nonlinear ones is still not well understood for distance correlation. Another note here is that distance correlation is a little bit slow, and scanning over these about 5,000 pairs will take about 3 minutes. So we can compare the speed here. So here's the R code, and let me first generate the random seed randomly. So the random seed is 5471. Now, with this seed, let's generate the data. Here it is. You can see the time matches my clock, so this is fresh. If you open the file, you see this is just like a dataset we handle every day. We have 256 rows and 100 columns. The first 10 columns, I know they are 5 pairs of bivariate normals. They are linearly dependent. Now, from this column on to the last column, there are 2 columns that are nonlinearly dependent. And my question for you is, can you see them? This is not so easy, right? Not so easy. It's not an easy task for me either. But now let's use the BET to find them out. We have coded the algorithm in Java GUI, so you don't need to know coding to use it. But we also have R package available now. Now let's load the data. Variables in column, row names and column names are present. Recall that distance correlation will take 3 minutes to do the test. So let's compare the speed. So BAT has it done in 3 seconds. Our C version of the algorithm is about 10 times faster than this. Now, how to find the two variables that are nonlinearly dependent? Note here that the linear dependency will be captured by interaction A1B1, so we can simply uncheck here to focus on nonlinearly dependent variables. So plot, and here we go. So the software says it's variable 65 and variable 85. They have more points in the dark region, and from the shape of the region, you can see the form of dependency is psi. But it's always a good idea to double check. So let's go back to R. We have recorded the indices and the scenario. So let's check that. So 65, 85, and psi. So it works. In 3 seconds, we can identify the two variables out of 100 who are nonlinearly dependent, and we can roughly identify the form of dependency. I am not aware of any existing statistical methods that can do this task in 3 seconds. So hopefully, with the BAT, we can save some time of our graduate students. And we did apply the BAT to the exploratory analysis of TCGA breast cancer data, where we do have about 10,000 gene expressions. We found this pair of genes to have an interesting behavior. The joint distribution shows a nonlinear dependency in this pattern. So why is this happening? To see that, we covered the subtypes of cancer. We found that for patients of this basal type of cancer, these two genes behave quite differently from the rest of the data. And if we mix the subtypes together, we create this nonlinear pattern. With the BAT, we can discover this pattern, and we can identify backwards these two interesting genes. An interesting fact here is that both of these genes are well known to be highly related to basal type of cancer. However, there's no research on their joint behavior yet. Our exploratory analysis basically suggests do that because the joint behavior contains a lot of important information. For example, if we just draw a line here, we can classify the subtypes of cancer with 91% accuracy. However, if we only use one of these two genes, the classification accuracy are not so great. So this is some new insights that BAT can provide. So this is the conclusion page. BAT offers a new perspective on non-parametric dependence detection. It's a combination of 3 classical statistical wisdom: binary expansion filtration, orthogonal design, and multiple testing. With only 2 main assumptions on IIT samples and continuous variables, we can have uniform consistency and minimax optimal power. We can have clear interpretability and efficient computation. The multivariate version of the BAT is available here. So here's the bottom line question. Can we tell if and how 2 continuous variables are dependent? My response, yes, you bet. Thank you very much for watching this video.